My name is Reuben Aronson, and I will be talking about our work on inferring goals with gaze during teleoperated manipulation. People with upper motor impairments have improved their lives greatly using robot manipulators. However, these harms are hard to control, especially using a low-dimensional input device like a joystick. Shared control aims to make this problem easier. First, an autonomous system predicts what the user's goal is. Then, the system generates its own plan to complete the task and fuses it with the user's input. These systems work well, but they rely on having a good prediction of the user's goal. Our insight is that people's natural eye gaze behavior during the task provides an informative signal for understanding their goals. Prior work on natural gaze during manipulation shows that the signal is highly correlated with what people are trying to do. People look at important parts of the task as they become important, and do so automatically without thinking about it. However, the natural gaze signal is difficult to use directly. Previous work on gaze for robot manipulation has focused on gaze as direct input, where people look at an object intentionally to convey their desire. With natural gaze, the assumptions that underlie that work are not supported. People's gaze is not directly predictable. While it follows overall trends, we cannot rely on users looking at specific objects at any particular time. To address these issues, we introduce sequential gaze modeling for goal inference. From raw eye gaze data, we first segment this data into individual fixations. Then, we label each fixation with the object in the scene that the user is looking at. Now that we have sequences of labels, we train hidden Markov models on these sequences, one for each possible goal. When given a new label sequence, we use these trained models to estimate the likelihood that the sequence would be produced by a user trying to accomplish each of the goals. By combining these probabilities, we obtain a prediction for the user's actual goal. We can see how this model works in detail here. On the left, we have a video of an actual trial, with key points and gaze fixations indicated. On the right, we have a plot of the prediction information throughout the trial. The top plot shows the prediction made by our sequential algorithm. It compares that prediction with the prediction made by an aggregate benchmark, which uses only the number of fixations directed towards each goal. The second plot shows the actual sequence of labels. The final plot shows the estimated hidden states assigned by the HMM corresponding to the correct goal. The states of the HMM enable the prediction to account for fixations towards other potential goals, which the aggregate model cannot handle. We compare our gaze-based sequential modeling strategy with the aggregate gaze model and an alternative joystick-based benchmark that takes in the user's control input instead of their gaze. We find that both gaze-based methods outperform the joystick-based method, with our sequential strategy performing best. In addition, we find that sequential modeling gives an earlier time horizon for accurate prediction. Thank you for listening. We encourage you to check out the paper for more information and to reach out to us with any questions.